And thank you, Alberto, because your talk was a very nice introduction to my own talk. And by the way, I promise I won't use UML in this talk, even though it hurts a bit because, as you may know, I like UML. So, what is the peculiar characteristics of C++? No, it's not undefined behavior. It's not operator overloading. It's something simpler. It's the simple, beautiful fact that C++ is multi-paradigm. It gives us the tools to program using the imperative, object-oriented, generic, metaprogramming, and functional paradigms. Think about it like building architecture. A building isn't made from a single material or technique. We use glass for the windows, concrete and steel for the foundation, and wood for the interior. Each part uses the right tool for the job, and C++ is exactly the same. Of course, many developers fall in love with one paradigm and stick to it, but it's not the best way to design our software, of course. Today, I want to show you how the fact that C++ is multi-paradigm gives us countless ways to pass behavior to a component. And why is passing behavior to a component so important? Because it's absolutely fundamental to achieving some essential non-functional requirement properties of our software, like usability, extensibility, and testability. So let's start. What is reusability? All right, this is a no-brainer. Everyone knows it. Software is reusable if you can reuse it as is in multiple places on the same application or across distinct code bases. Let's say I have this function, just sort some objects. But if I want to reuse it in different contexts, I probably need a way to inject the sorting criterion. I might also want to make a class reusable. For example, a button widget in a GUI library. If I can specify what should happen when the button is pressed, I would need a different class for every button in my application and for every button in every application. So once again, I need a way to inject a behavior. Finally, we might want to reuse a bunch of classes, which would be the most valuable kind of reuse. This is the general picture of reuse. When we want to reuse a component, either within the same application or across different ones, it's very unlikely we can just reuse it as is. Most of the time, we need to customize some part of its behavior. That's why we need a mechanism to inject behavior into the component. Extensibility is a bit trickier. It's not as popular as reusability, but it's incredibly valuable in real-world projects. It means basically that I can take an existing program or component and add new features or behaviors with minimal changes. Sometimes with no changes at all, just by adding a new source code, a new source file to the project, or even by loading a dynamic library at runtime. We don't hear much about it, probably because most conference speakers live in a world of small libraries, not in the mass reality of big real-world projects. So how do we make this possible? By designing an application where behaviors can be customized. In other words, by injecting behaviors that weren't originally anticipated. Then we have testability. Testability means that a component can be tested without any modification. And if you think about it, in the case of unit tests, it's really a form of reusability. We just want to reuse the component in a test environment. In the case of integration test, instead it becomes a form of extensibility. We test the whole system, but we extend it with test doubles for I/O or hardware. So we need a way to pass behaviors because we pass it as a parameter, and we can inject alternative versions like mocks, stubs, or spies for the testing. So let's go to the point. In C++, what can I pass as a behavior? A free function is a behavior. A lambda is a behavior. A functor is a behavior. A polymorphic object is a behavior. Well, actually, it's more than a behavior because you can have multiple methods and you can pass multiple behaviors. And by the way, in this case, I wouldn't use polymorphism, but I just wanted to reuse the example of the previous part. Okay, so we've seen what I can pass as a behavior. But now the question is, what type of formal parameter should I use in my function to accept those behaviors? The oldest one is we can expose a parameter of type function pointer. In this case, we can pass a free function or a stateless lambda because it's implicitly convertible to a function pointer. And by the way, please note that member function pointers aren't very useful here because they fix the behavior. You can just change the instance, but the behavior is the one you specify in the signature. Next, we can expose a pointer to an interface, to a polymorphic interface, and this gives us runtime polymorphism, and where the behavior can change depending on the actual object we pass. In this case, you need to manage the lifetime of the object, and by the way, it doesn't need to be on the heap, but someone has to make sure it stays alive while it's being used. We can use a template parameter with concept that can accept any callable type. Here, the behavior is fixed at compile time, so the compiler can inline and optimize everything. So this gives us a zero-cost abstraction. But of course, there are some trade-offs. You can't easily store or reuse this behavior because the type depends on the callable. The template must be defined in the header file. And the code size may increase if you use many different callables. Then we can have a parameter of type stud function that allows us to pass any kind of callable, lambdas, functors, or function pointers. Unlike templates, it provides a uniform, copyable, and storeable type. So you can store it in containers, assign it, or even reassign it at runtime. The trade-off is a small runtime overhead because, unfortunately, the compiler can't inline it. We'll see it later. Then later, it's become quite trendy to use stud variant with stud visit, especially as a replacement for virtual functions. And for everyone who's been living in a bunker for the last few years, a stud variant is basically a type-safe union, and that can hold a fixed set of types, and stud visit lets you perform an action depending on which type it currently holds. In this case, we get a type-safe runtime dispatch, and the trade-off is that it's compiled into a jump table, so we have some kind of runtime overhead. So this table summarizes what we can offer in our interface and what kinds of behavior we can actually pass, along with their compatibility. On the rows, we have the type of the formal parameters, and on the columns, we have the types of behaviors we might want to pass. Each mark at the intersection tells you whether the combination works. For example, please notice that the only way to pass a lambda is either to use stud function or to make the parameter a template. Now, I know what you all want. Yes, I know what you all want. You want speed. You want your code to be blazingly fast. Maybe that's why you choose C++ in the first place. So let's talk about the tricky subject of speed and benchmarks right away. But before to do that, I need this solemn promise from you. You will not take the following results too seriously and as a qualitative results only. Because the next slides are not about who's faster. They're here just to show you how each technique works and what's happening under the hood. So let's look at the highlighted cases. We're going to measure them using a simple micro benchmark. Basically, we want to see how long it takes to call a behavior depending on how it's passed and what kind of wrapper or mechanism we use. Okay, these are my results. And in this chart, shorter is better. I use the same simple behavior everywhere, just multiplying two integers, and compile with GCC at optimization level 02. I even check the assembly, the resulting assembly, to be sure that there was no inlining, because what I really wanted to measure was the intrinsic cost of each mechanism. And inlining can completely hide those differences. And by the way, sometimes the compiler cannot inline the code, so that for the same reason, I also avoided the virtualization and guarded the virtualization. so that every call would actually go through the intended dispatching mechanism. And I honestly got more or less what I expected. So let's see the results in detail. The first two measurements serve as a baseline for the rest. They are two simple direct call to the same function, the one that just multiplies two operands. The first is inline, and the generated code, if you see, is just basically the multiplication, and one operand is already in a register, and the other one is loaded from memory. And we have no call, no overhead in this case, and you can expect. In the second case, I have the non-inline call function, and we set up the two parameters in the registers according to the calling convention, and then the call to the function, to the multiplication function. The processor doesn't need to read memory to know where to jump. The branch predictor can easily predict the destination, and the call can be inline if the optimizer works. Now, when we call the function to a function pointer, things change. The call becomes indirect through memory, and the CPU first has to read the function's address from memory, and then it can jump to it. This means we add a memory access, makes branch prediction harder, and prevents the compiler from inlining the call. So, unsurprisingly, it's slower than the direct call. Oh, by the way, if we pass a lambda, the code generated is exactly the same, but we call the pointer to the closure generated by the lambda, that in this case is just a function because it's not state. There's not state. Next, we have the virtual function. Okay, just like before, the generated code loads the parameters from memory and puts them into registers. Then we have the third assembly instruction, a move from R14 to the register AX. So, R14 contains the pointer to our object, so that it's this pointer. Now, what's the very first thing we find inside an object that has virtual functions? The v table, exactly. So now, RAX contains the pointer to the v table. Then we have move RDI into R14, into RDI. And according to the calling convention, RDI is the first argument to member functions. In this case, being an object is this pointer. And finally comes the key instruction, the call to the address RAX. That's actually our virtual call. So we are doing an indirect access to the v table, which means another memory read. Branch predictor can't work because the prediction becomes harder, and inlining is impossible unless you have maybe just one type of this hierarchy, and so the compiler can understand that you have just one possibility. Now, where does the case with a template parameter fit in my benchmarks? Okay, it depends. Depends on what I pass to it, of course, a regular function, a functor, or a lambda. By the way, without aggressive optimization and without inlining, which one do you think is faster according to the generated code? Okay, let's take a look. Of course, inside the compiler generates different version of our function foo. If I pass a function, the compiler generates a version that takes a function pointer. If I pass a functor, it generates a version that takes the object type directly. And the same happens with a lambda. The compiler generates a version that takes the closure object to the created from that lambda. So in the first case, the call goes through a function pointer that is an indirect call. In the other two cases, it's a direct call. So calling a lambda or a function in a template is the same as a direct call, maybe even inlined. While calling a function in a template is the same as a call to a function pointer. That means that passing a function to a template can actually be slower than passing a lambda. Okay, I guess I've missed a slide before where I explained what happens when we pass a function pointer. So let's go back. Sorry. This slide, maybe I've missed it before. No? Okay. I explained that. Okay. So we have. Okay. So since we know that passing to a function pointer is slower than passing to a functor, for example, we see that passing a function to a template can actually be slower than passing a lambda, because you go through the function generated by the compiler takes a function pointer. Now we can also understand the performance behavior of a call to a stud function. So no matter what it contains, the first thing that happens is a call to the operator parentheses. That operator performs type erasure, dispatching, using a virtual function belonging to a templated internal type that was instantiated for the original callable. That virtual function finally calls the actual callable object. So regardless of what's inside the stud function, these first steps are always the same. What changes is how the original callable is finally invoked. If it contains a function, the call still goes to a function pointer, that is an indirect call. If it contains a lambda or a functor, it's a direct call. This explains why stud function containing a function is actually slower than the same stud function containing a functor or a lambda. And you can see here. Here you can see that lambda functors come out a bit faster than function. They should be identically in theory, functors and lambdas, but you know how benchmarks are. What's interesting, though, is that in all the cases with just one single level of indirection, function pointer, virtual call, or stood function with a lambda are pretty much the same, are very close in performances. Finally, let's see what happens when you pass an object containing some behavior to a stood variant, and then you use stood visit. The compiler generated this instruction in this way. It creates a static table with one entry for each type in the variant. Each entry contains a small function that calls the visitor, passing the value of the active alternative. And at runtime, the correct function is selected using the variant index. And then function then invokes the visitor with the appropriate type. For example, this is a typical type where Gauss shows that virtual function can be replaced by stood variant with stood visit. The visitor is a generic lambda that calls the draw function. And each element of the jump table calls the appropriate call operator of our generic lambda, which in turn calls the draw method of the correct object. So you have two calls, maybe inlined. In this case, you can see the last two bar chart. So in this case, the first thing that happens is the check of the index inside the variant. Then the CPU has to jump to the corresponding case in the jump table. Then the operands are loaded, the lambda is called, and the correct function is finally called, possibly inlined, if the compiler can manage it. So you can see here that the inline version is more or less similar in performances with virtual function, stood function, and function pointer. And if the compiler cannot inline the function, the performances are much worse than the others. So let's wrap this part about micro benchmarks. So the results are influenced by three main factors: library optimization, compiler optimization, and hardware effects. The first one, I think, should be part of the measurement because it's part of the mechanism itself. Compiler optimization depends heavily on how you use the code. In my benchmark, I avoided them so we could see the intrinsic cost of each technique. And hardware effects instead can be really generalized. They vary from one CPU to another and from case to case. So micro benchmarks doesn't really measure your program. They measure the benchmark itself. And actually, they're pretty meaningless from my point of view. I use them just to give you an idea of what's happening under the hood. And surely not to claim that one construct is always faster than another. So, and the speed of your code depends heavily on the many factors that you can't possibly isolate in a micro benchmark. Of course, the right way to optimize your code is to profile it and not performing benchmarks. So you can profile your whole application, find the critical parts, try to optimize it, and then measure again, profile. And performance can anyway vary with compilers, versions, flags you pass to the compilers, CPUs, load, execution path. What is stable instead are the design properties of the code and the mechanism. So now let's focus instead on the properties of the language construct. When we pass a behavior, sometimes we need to remember something, a little bit of context, a partial state of the computation. Well, a free function doesn't remember anything by itself, unless we cheat using global or static data, and that's usually a bad idea. Lambdas change everything because they can capture local variables to the capture list by copy or by reference. And there is a subtle tension between the capture list and RAII, because if you capture something by reference and the object goes out of scope, you've just broken the mechanism. So capturing by value is safer, of course, but now we are creating a copy of the object. Then we have functor, polymorphic object, and stud variant that contains object, that being object can contain state and share state between their method. Let's talk now about scattering versus gathering behaviors. So when you pass a function or a lambda, you're basically passing just one thing, one behavior at a time. Well, of course, on the other hand, if you pass an object, functor, a polymorphic object, or stud variant, we are passing one or more related behaviors, and they can actually share state and group coherent logic. So the simple guideline here is if behaviors belong together, keep them together and don't scatter separate functions around, write them into a single object. To put it another way, with function or lambda, you pass a piece of logic to execute. And with polymorphic object, functors, or variants, you pass a value that embodies the behavior itself. In the second case, the choice of behavior travels with the data. Okay. Now, let's say we have a component that we need to customize through a policy. Let's start with the first case, which I like to call a throwaway policy. That's the easy one. The policy is used immediately inside a single method, and we don't need it anymore afterwards. It could be any callable or class as long as we only apply it here, and the implementation is trivial, just template the method. So this is the easy case, and the second case instead is much harder. I need the policy multiple times later. So the question becomes, how can I store the policy? We have basically two ways to do it, and a static one and a dynamic one. Okay, the first solution is the classic one. just make the class itself a template. We have on the plus side, it's a zero cost abstraction. The compiler can inline everything, optimize everything, and it works with all the callable types, lambdas, functors, stateful object. And the downside is that each policy produces a different type, and that the policy is fixed at compile time. This is a variation on the previous approach known as policy-based design. It was introduced by Andrei Alexandrescu 25 years ago in his seminal work Modern C++ Design. And the idea is that you define the behavior of a class through template parameters called policies. Here then you can inherit privately from the policies. And in this way, you can build classes with highly customizable behavior, and it's all resolved at compile time without using virtual functions. By the way, this is not really about passing behavior, it's more like about composing behaviors at compile time, okay? Okay, the other option we have to store our behavior is to use some kind of type erasure. For example, we can store the behavior in a stud function. In this way, the class doesn't depend on the policy anymore. You always have the same type, in this case user repository, regardless of what behavior you inject. You can even replace the policy at runtime, which sometimes is very handy. And of course, this comes with some trade-off. There's a small runtime overhead, possibly heap allocation, but this has more to do with passing stud function than calling it. And of course, you lose compile time inlining in this case. Of course, we have also the classical approach using a polymorphic interface and object-oriented polymorphism, also called inclusion polymorphism. This is actually the oldest of all these techniques, so that it was a gang of four pattern called strategy in the design pattern book. Okay, I guess it's pretty known, so that yes, the good part is that it's flexible. The class type does not depend on the policy, of course. You can replace the policy at runtime this time. It scales well because if you need to add more behavior, you can add it to the interface. Of course, you have a small runtime overhead due to the indirect call, and it can't be inlined. So, just to recap, how do we store a behavior? With all the cases here, function pointer, interface, stud function, variant, we can store the behavior directly. With the templates, you need some form of type erasure, or the whole class must become a template. Then, sometimes we need to change the policy, the behavior at runtime. For example, these are some cases where you cannot avoid it. For example, when you rely on some user-defined configuration, when you need some plugin architecture, you must react to some variable condition, so you can change the algorithm depending on the condition of your environment. For testing is another thing. And of course, with a template interface, you cannot change the behavior at runtime. Another key limitation of templates and stud variant, in particular, is that the set of the type you can use is fixed at compile time. Once the code is compiled, you can't add any new alternatives. This means that this approach doesn't work well in plugin-based architectures, and where you need a true runtime extensibility. Using a stud variant, you can actually change at runtime the behavior, but you cannot extend the set of the behavior dynamically. But one of the main limitations of template class is, from my point of view, template propagation. This, for me, is the biggest problem of template in real-world project. When I use a polymorphic interface or a stud function inside a class foo, the dependency is encapsulated inside the class. So whoever uses foo doesn't need to know what implementation or behaviors is inside, they just use foo. Only the creator of foo needs to inject the behavior, and so it needs to know which behavior is used. Every other client doesn't need to know. But when I use a template class bar t, for example, the dependency becomes part of the type itself. So everyone who wants to use bar must either depend directly on the specific instantiation, like in this case, bar of concrete policy. And this isn't great for policies because the whole point of policies is to hide the concrete behavior and make it swappable. If clients depend on a specific policy type, you lose that flexibility. So the other case is that the clients become template too. This effect can cascade, of course. Your template's parameters multiply as you compose types and policies. And another bad consequence is that everything usually ends up in header files because templates need to be fully visible at compile time. In short, templates expose dependencies, whilst interface hide them. So, while templates are fast and zero cost, they come with a cost in code structure and compile time management, if it worries you. So to wrap up this part, when you should use a template for passing behavior? Well, you can use it if you need maximum performance and if the code is confined to a subsystem where you can control the types. Otherwise, stick with polymorphism or stud function or some kind of type erasure, which gives you runtime flexibility and composition with a small overhead. In practice, most of the system uses hybrid approach where you have templates internally where performances matters, and you can keep things contained and then expose a type erased interface or virtual API and the subsystem boundaries. That way you get the best of both worlds. So, to recap, we've seen why passing behavior matters, the main technique C++ gives us to do it, how they work under the hood, a rough idea of their performances, and a glimpse of their design implication. There will be so much more to say about the last part, but that would take the whole day. So, what I'd like you to do starting tomorrow, starting Monday, is to think about the alternatives before writing code and consider the design consequences first. Don't just pick a technique just because everyone says it's faster. First, not every piece of code needs to be fast. And second, performance always depends on context. Until you measure it in your own code, you don't really know. And remember, C++ is a multi-paradigm language. Don't limit yourself to the one technique you're most comfortable with, and don't build your whole house out of glass, including the foundation. Oh, and as I promised, okay.
Any question? I guess everyone wants coffee.
Okay. It was clear. Clear enough.
I'm not sure if the benchmark you show us could vary depending on the standard you use for programming. Or
the standard version of C++, you mean?
No, I mean if the times you present as now. I think for certain features like the variant, you cannot use every standard. But a feature that, for instance, is available for different standards, versions of the C++, it is possible that the times vary because some optimizations are added, but you say,
yes,
you told us that you avoid the optimizations,
yes.
But it's possible also somehow that the measures get dependent on the version of the standard, I mean.
Yes, thank you. All my benchmark was tried using C++23 with GCC on x86. I checked the assembly to be sure that all the optimization of stud visit was applied. So my benchmark is what you should get by using in your application C++23 with O2 optimization with GCC, of course, but I tried also Clang and it's pretty much the same. The only thing that changes between Clang and GCC is that Clang translate translate always into a jump table, even if you have just 2 types. Whereas GCC, until 12 types, uses a switch case. And then after 12 types inside the stud variant, uses a jump tables. And so you can see varying the number of types contained in the stud variant, you can see slight worsening in the speed for the first for the first 12 element, and then it becomes constant. Instead, with Clang, it's constant. But I've seen in talks in other conferences that I've seen benchmark that shows that stud variant with stud visit is better than virtual calls. But I'm sure of my benchmarks. I checked the assembly generated, and even with inline, it's more or less the same as virtual function. I've not seen improvement, but as I've said before, the benchmark is not your application. Benchmark measures only the benchmark. It's just, I was intrigued by looking inside the benchmark because I understood how these constructs were translated in assembly. I understood many things about compiler and variant in this way, but the result of the benchmark itself, I can be sure. But if any of you want to talk with me about the benchmark, we can see together the results.
Thank you.